Hello, and welcome in. This is Echoes of the Forgotten Earth, a quiet place at the edge of the map where we don't rush the story just because the world is in a hurry. Wherever you've arrived from, late at night with the room dim and still, or early in the morning with the day not fully awake yet, I'm glad you're here. Tonight we're stepping into one of the longest running patterns on this planet, a pattern so slow it hides in plain sight. It doesn't explode like a volcano. It doesn't flash across the sky. It doesn't even announce itself the way a storm front does. It simply takes its time. If Earth had a heartbeat you could hear, this would be part of it. A low, steady rhythm that comes and goes on a schedule no human being can feel in their bones, but that every mountain valley, every coastline, every soil layer, and every migrating species has learned to live with. We're talking about the strange way the planet drifts into deep cold and then, just as patiently, climbs back toward warmth again and again. Not every few centuries, not every few millennia, but on timescales that make the entire span of recorded human history look like a brief flicker at the edge of a much larger night. Roughly every 100,000 years, give or take, the great ice sheets swell outward and then withdraw. They advance like a slow tide of stone-white silence. They retreat like a long exhale. And in between those two movements, the world we recognize is rebuilt, sometimes gently, sometimes violently, always persistently. It's tempting to imagine that ice ages happen because something suddenly goes wrong, because a single catastrophe knocks Earth off balance. But the deeper truth is stranger and quieter. The planet isn't stumbling into cold at random. It's responding to patterns written into its motion through space and to feedbacks within its own oceans, air, ice, and living skin of forests and grasslands. The cold is not an accident, and the warmth isn't either. Before we drift too far, it helps to hold one humbling thought steady in your mind. Everything we call normal climate is, by geological standards, a temporary arrangement. The era that allowed civilizations to rise, fields planted year after year, coastlines used as borders, cities built where rivers behave predictably, is an interval of relative gentleness. A warm pause. A stretch of time where ice has largely pulled back, where sea level has been high, where the big northern continents have been mostly free of the kind of ice that can flatten terrain and redraw drainage basins. Human beings, as we know them, learn to become human in the aftermath of cold. We learn to travel during shifting climates. We learn to survive on a planet that was still adjusting to ice. And then, during an unusually stable warmth, we built the world that now feels permanent. But on Earth, permanence is often just a long-lived illusion. To understand why the planet keeps slipping into glacial cold, you have to step back far enough that the familiar year-to-year changes stop being the main story. The seasonal wheel spring, summer, fall, winter, is real, but it's only the surface layer. Beneath it is another kind of seasonality, one that stretches across tens of thousands of years. A geological year, a climate year, a cycle so long that no one can stand at the beginning and live to see the end. And yet the cycle leaves evidence everywhere. It's written into the shape of valleys that look too wide for the rivers they hold. It's pressed into the landscape as ridges of debris left by moving ice. It's preserved in microscopic chemistry inside shells on the seafloor and in bubbles of ancient air trapped in ice that fell as snow long before our languages existed. It's echoed in the fact that sea level has not been steady. It has risen and fallen like a slow breath, sometimes exposing land bridges between continents, sometimes drowning them again. The world has not been a fixed stage for life. It has been a moving stage, sometimes sliding, sometimes tilting, sometimes narrowing, sometimes opening into entirely new shapes. So why does it happen? Why does Earth freeze and thaw with a rhythm that's so persistent, so recognizable, that we can trace it backward like rings in a tree? The beginning of the answer is not on Earth's surface at all. It's in the way the planet moves around the sun. We're used to thinking of Earth's orbit as a neat circle, like a diagram in a classroom. One loop per year, a steady routine. But the real orbit is slightly stretched, and that stretch changes. Earth's axis leans, and that lean changes. And the axis doesn't just lean, it slowly swivels, like a top that never quite stops turning. None of these motions are dramatic in a single lifetime. They don't give you a new season next year. They don't cause an instant freeze. But they do something subtler. They change how sunlight is distributed across the planet, where it lands, when it lands, and how intense it is during the season that matters most. And the season that matters most is not winter. That surprises people, because ice ages feel like stronger winters. But the critical question for building an ice sheet is not how cold January gets. The question is whether summer is strong enough to erase what winter left behind. Snow can fall in a climate that is, on average, not extremely cold. Snow can even fall heavily. What determines whether ice builds year after year is whether the summer sun can melt it away. If summer is just a little too weak, just cool enough, just brief enough, just indirect enough, some snow survives. It lingers in shaded hollows, on plateaus, on northern slopes. That leftover snow becomes next year's foundation. It compacts. It turns grainy. It hardens into ice. And then the planet begins to change its mind about what normal means. At first, the changes would be almost insultingly subtle. Not the kind of difference you'd notice with your eyes. More like this. The snow line sits slightly lower. The melt season ends a few days earlier. In one region, a small glacier doesn't retreat as far as it used to. In another, the tundra pushes south by a slow, steady negotiation with the forest. Year after year, those tiny negotiations add up. Ice is not a quick thing. It does not arrive with drama. It arrives with persistence. It is patient. It does not need a single catastrophic push. It needs only a long series of summers that fail to do their job completely. Once some snow remains, the feedback begins. Snow and ice are bright surfaces. They reflect sunlight back into space. That reflection means less heat is absorbed by the ground. Less absorbed heat means cooler local air. Cooler air means more snow survives. More snow surviving means an even brighter surface. The loop tightens slowly, like a knot being pulled a little firmer each year. That reflective effect albedo sounds technical, but it's easy to feel if you've ever walked outside on a sunny winter day. The light doesn't just shine. It bounces. It fills your eyes. It turns the landscape into something stark and luminous. Now imagine that brightness spread over half a continent. Imagine it lasting not for weeks, but for millennia. A small initial cooling, driven by how sunlight is distributed, becomes a self-reinforcing shift. And once ice starts to build, it changes more than the color of the ground. It changes the behavior of the atmosphere. It changes winds. It changes storms. It changes where moisture travels and where it falls. Even the oceans begin to rearrange themselves. This is where the story becomes less like a single cause and more like an ensemble. Earth's long climate swings aren't controlled by one dial you can turn. They're shaped by a cluster of interacting mechanisms: orbital geometry, ice feedbacks, ocean circulation, greenhouse gases, dust, vegetation, sea level, the slow rebound of land under the weight of ice. Each piece can strengthen or weaken the others. Sometimes they synchronize, sometimes they fight. When they synchronize, the ice grows with quiet confidence. The broad rhythm most people have heard of, something like every 100,000 years, is real in the recent geological record. The most recent million years or so have been dominated by glacial cycles with a rough 100,000-year pacing, long cold buildups, then comparatively shorter warm intervals. But the rhythm isn't perfectly metronomic. It's more like a recurring theme in a long piece of music, recognizable, repeating, but with variations each time. And there's a deeper twist. This wasn't always the dominant rhythm. If you travel farther back, beyond the most recent million years, the climate cycles were paced more strongly by a different beat closer to 40,000 years, tied tightly to changes in Earth's tilt. Then, something shifted. the system began favoring the longer 100,000-year pattern. Scientists still argue about why, and the arguments are not trivial. They touch ice sheet dynamics, ocean carbon storage, thresholds, and slow changes in the background state of the planet. We'll come back to that, because it's one of the most intriguing chapters. Not just that Earth cycles, but that the style of its cycling can change. For now, let's stay with the basic idea. Earth's climate has long memory, and it is shaped by slow geometry. The planet's orbit is not a perfect circle. It slowly becomes more circular, then slightly more elongated, in a cycle that takes about 100,000 years. That change is called eccentricity. When the orbit is more elongated, the distance between Earth and the Sun varies more across the year. When the orbit is more circular, the difference between closest and farthest is smaller. That distance difference does not change the total sunlight Earth receives by a huge amount. It isn't like the sun turns off or on, but it matters because it changes seasonal intensity when combined with other motions. It can amplify the effects of Earth's axial wobble, which changes when the seasons happen relative to where Earth sits on its orbit. The tilt about 23 degrees today also shifts over time. It swings gently between a little more and a little less over roughly 41,000 years. A bigger tilt makes seasons more extreme, warmer summers and colder winters, especially at high latitudes. A smaller tilt makes seasons milder, cooler summers and less intense winter contrasts. And again, for ice sheets, cooler summers are the dangerous ingredient. They're the ones that leave behind what winter deposited. Then there's the slow wobble of Earth's axis, called precession. It takes about 26,000 years for the axis to trace a full circle in its orientation. Precession doesn't change the tilt angle itself. It changes the direction the tilt points. That matters because it changes whether a hemisphere's summer happens when Earth is closer to the Sun or farther away. Today, Earth reaches its closest approach to the Sun perihelion during the Northern Hemisphere's winter. That means northern winters are slightly milder than they'd otherwise be, and northern summers are slightly cooler than they'd otherwise be, because summer happens when Earth is a bit farther away. But precession shifts this arrangement. Thousands of years from now, northern summer will occur closer to perihelion, and northern summer sunlight will be slightly stronger. Thousands of years after that, it will swing back. All of these cycles, the stretching of the orbit, the changing of the tilt, the wobble of the axis, alter the distribution of sunlight. Not the total yearly amount in a dramatic way, but the regional and seasonal intensity in ways that matter profoundly when repeated. Here's the quiet, stubborn truth at the center of the whole mystery. Ice ages are born from small changes that persist. Not from one bad winter, not from one unusual decade, but from thousands of summers that are just a little less effective at melting. And because the planet's continents are arranged the way they are, the Northern Hemisphere becomes the key stage. The North has large landmasses at high latitudes: Canada, Scandinavia, Siberia. Land is where ice sheets build most easily because snow can accumulate layer over layer. Over ocean, ice tends to float, drift, and melt from beneath. Oceans also buffer temperature changes, absorbing and releasing heat more slowly. Land warms and cools quickly. Land can lock in snow if summer weakens. Land can hold an ice sheet in place. So the North becomes the workshop where glaciation is built. When northern summers weaken enough, through the right combination of orbital conditions, snow survives. Bright surfaces expand. Cooling deepens. Ice thickens and spreads outward. Sea level drops as water is locked away on land. Coastlines shift. Continental shelves emerge. Land bridges appear where waves once moved, and life responds. Forests retreat. Grasslands expand in some regions. Tundra spreads. Animals change their ranges. Migrations redraw themselves across continents. Even humans' early, adaptable, persistent found routes opened by lower seas and climates on the move. The story of our species is stitched into the seams of glacial time, the opening of corridors, the closing of them, the pressure to innovate, to follow herds, to find refuge, to endure. During the last great glacial maximum, Enormous ice sheets covered much of what is now Canada and the northern United States, as well as large portions of northern Europe and parts of Asia. In some places, the ice was thick enough to crush the land beneath it, depressing it like a weighted mattress. Mountains were softened under moving ice. Valleys were carved wider, deeper, and smoother than rivers alone could manage. When the ice finally retreated, it left behind a rearranged world. Moraines piled like raw edges of stone. Lakes filling basins gouged by glaciers, rivers diverted, coastlines advancing inland as sea level rose. The land itself began to rebound upward slowly, still rising in some regions today because the weight of ice had been removed. And what is remarkable is not just that this happened once, it is that it has happened again and again, with enough regularity that we can trace it in the archives Earth keeps. Those archives are patient too. Ice cores drilled from Greenland and Antarctica preserve layered snowfalls compacted into ice, trapping bubbles of ancient air. Those bubbles hold the atmosphere of the past carbon dioxide levels, methane levels, tiny hints of temperature. Ocean sediments accumulate shell fragments from microscopic organisms whose chemistry shifts depending on temperature and ice volume. Layer upon layer, the seafloor keeps a long diary. Rocks and soils preserve pollen grains that show what kinds of plants lived where and when. When scientists read those diaries together, a pattern emerges. Long glacial buildups and shorter warm releases. A rhythm shaped by orbital geometry and amplified by Earth's internal feedbacks. And it's those internal feedbacks, the planet responding to itself, that make the story feel less like clockwork and more like a living system. Because even if orbital cycles provide the pacing, they do not act alone. The climate has inertia. Oceans move heat with deep currents that respond slowly. Ice sheets have mass and elevation, and their own internal behavior flow. Sliding, cracking, melting at the edges, accumulating in the interior. Greenhouse gases rise and fall as oceans breathe carbon in and out, as dust fertilizes plankton, as vegetation shifts, as soils freeze and thaw. It's a complicated choir, but the chorus keeps returning. And it returns because small changes in summer sunlight, repeated for long enough, can tip a delicate balance. Once tipped, the system begins to reinforce itself, cooling, inviting more cooling, ice inviting more ice, until an enormous state change has occurred without any single moment you could point to and call the beginning. That's one of the most unsettling and beautiful parts of the story. If you lived through the start of an ice age, you wouldn't know it. Not the way you know a storm has begun, not the way you know an earthquake has happened. You would see only a run of slightly cooler summers, a little more lingering snow in certain shaded places, a subtle shift in what grows where. But if you could return thousands of years later, you would find a different world. And if you could watch the whole process on fast forward, if continents could be seen breathing, then you would see the ice advance like a slow, white inhale, and retreat like a long, thawing exhale. That's where we're going. In the next part, we'll step more carefully into the mechanics of those orbital motions, tilt, wobble, and the changing shape of the orbit, but always with the grounding question in mind. How can such small celestial shifts end up building ice sheets thick enough to remake the world? We'll move at the pace the planet prefers, quietly, steadily, without rushing the age of ice. If you want to understand the long freeze, you have to do something that feels a little unnatural at first. Stop thinking in the span of a single human life. Our instincts are built for quick causes and quick results. We register a cold snap, a stormier season, a strange stretch of heat, and we hold on to those memories because that's the scale we live in. But the machinery that builds an ice age isn't impressed by a bad decade. It doesn't care about the difference between one generation and the next. It cares about accumulation, about what happens when a tiny imbalance repeats so many times that it stops being tiny. Picture stacking sheets of paper. One sheet is nothing. 10 sheets are still almost nothing. 1,000 sheets becomes a block you can feel with your hand. 10,000 becomes something that changes what fits on the table. Glaciation is the climate system stacking its sheets, season after season, until the pile changes the room itself. That's why the real gatekeeper isn't winter, it's summer. Winter can be fierce and still fail to produce lasting ice. Winter can bury a landscape, lock up rivers, and turn the world white for months at a time. And yet the whole thing can vanish again if the summer sun arrives strong enough to do its cleanup. The surface darkens, it absorbs heat more easily, and the cycle resets. For a major ice sheet to begin, you need summer to fall short, barely, but reliably. Not once, not a handful of times. You need thousands of summers that are a little less effective at melting what winter laid down. And the place where that shortfall matters most isn't the equator, and it isn't the tropics. It's the high latitudes, especially across the Northern Hemisphere, where the long summer days can either deliver powerful melt or under slightly different geometry deliver daylight that lasts and lasts, but doesn't quite have the strength you'd expect. The subtlety is this. Sunlight isn't only about how many hours it shines. It's also about angle. Up north, the sun rides low even in summer. Its light comes in slanted, spread thinner across the ground, filtered through more atmosphere. So if you adjust the angle a little, or the distance a little, or the timing of the seasons a little, you can change the melt budget of an entire region. You can alter whether snow clears completely, or whether a small remainder survives into the next year. That's what the orbital cycles really do. They don't dim the sun like a lamp turned down. They shift where the sun's energy lands, when it lands, and how intense it is at the exact time and place that decides whether snow is erased or preserved. Earth's axis leans, and that lean isn't perfectly fixed. Over tens of thousands of years it swings through a narrow range, only a couple of degrees. Yet that slight change decides how sharp the seasons are in the high latitudes. When the lean is a bit larger, the seasons intensify. High latitude summers get a stronger dose of sunlight. Winters get darker and colder, but the stronger summers tend to melt away what winter builds. When the lean is smaller, the seasons soften. Winters are still cold, but the crucial change is that summers lose some punch. And in a world where ice is decided by summer melt, that matters. At the same time, Earth's axis doesn't just lean, it slowly swivels. It traces a long circle over many thousands of years, a steady wobble that changes the direction the axis points. That wobble shifts the timing of the seasons along Earth's orbit. Because the orbit is slightly elliptical, Earth is a bit closer to the Sun at one part of the year and a bit farther at another. The wobble decides whether a hemisphere's summer happens closer in or farther out. A summer that falls when Earth is farther from the Sun is slightly weaker. A summer that falls when Earth is closer is slightly stronger. On its own, it's not a dramatic difference. Over thousands of years, it can be the difference between snow that disappears and snow that stays. Then there's the slow change in the orbit's shape itself. Earth's path becomes a little more circular, then a little more stretched, over a cycle that plays out across roughly 100,000 years. This doesn't radically change the total sunlight the planet receives over a year, but it changes how important that wobble becomes. When the orbit is more stretched, the difference between closer and farther is larger, so the timing of seasons matters more. When the orbit is closer to circular, the distance difference shrinks, and the timing has less leverage. In that sense, the long change in orbital shape acts like an amplifier knob. It doesn't write the whole song, but it can make the other notes carry farther. All of this affects the whole planet, yet the story keeps circling back to the north for a reason. Earth isn't arranged symmetrically. The Southern Hemisphere has Antarctica, an immense, long-lived ice sheet perched on a high, isolated continent, surrounded by ocean that buffers temperature swings. The North, by contrast, has broad land masses reaching deep into high latitudes. Land is where snow can stack. Land is where ice can grow thick without drifting away. Land can hold an ice sheet in place long enough for it to become a force of its own. So when northern summers weaken enough through the right combination of lean, wobble, and orbital shape, snow starts surviving in places where it used to melt away. Small bright patches linger, the surface reflects more sunlight, The ground absorbs less heat. The air above cools a little. The next summer has a slightly harder job, and the year after that, harder still. This is how deep time weather begins, not with a headline moment, but with a statistical drift. A slow change in the distribution of summer warmth, too small to feel year to year, large enough to matter when repeated for millennia. You see it first in stubborn snowfields that refuse to vanish. You see it in the quiet migration of plant boundaries. You see it in permafrost that creeps farther south. And you see it in the moment the climate starts preferring reflection over absorption. Once enough snow lasts long enough, the system begins to reinforce itself. Bright surfaces expand. And that brightness is not just a detail, it's a climate lever. Sunlight that would have warmed dark soil or rock now bounces back to space. Less warming means more snow survives. More survival means more brightness. The loop tightens gradually, then more confidently, until a few leftover patches becomes the early architecture of an ice sheet. And ice is not passive. It doesn't simply sit there as a result of cold. It changes the world while it grows. As it thickens, it lifts its surface higher into colder air, making itself harder to melt. It cools the air passing over it, changing pressure patterns and redirecting winds. It nudges storm tracks, which are the couriers of moisture, and moisture is the raw material of snowfall. Some regions become snow-fed engines of accumulation. Others dry out, not because they are warmer, but because cold air holds less water and storms travel different routes. As ice expands, it locks away water that used to be in the sea. Sea level drops, not by inches, but by tens of meters, sometimes more. That exposes continental shelves. It changes coastlines. It opens land bridges and closes shallow seas. And those geographic changes can reshape ocean currents, which reshapes heat transport, which feeds back into the climate again. The oceans, in particular, give the entire system a kind of stickiness. The atmosphere can change quickly. The ocean is slow. It stores heat and releases it reluctantly. It moves warm water poleward and returns cold water to the depths in patterns that can shift, but only over long spans. When the surface cools, the ocean can absorb more carbon dioxide from the air, lowering greenhouse warming and reinforcing the cooling that started with weaker summers. During warming phases, the reverse can happen. Warmer water releases carbon dioxide, strengthening the greenhouse effect and helping the thaw take hold. This is part of why ice ages have depth. Orbital geometry can tip the balance, but the ocean and carbon cycle help determine how far the planet will go once it tips. And Earth keeps records of this, not vague memories records you can drill into and measure. Ice cores hold ancient air sealed in bubbles, preserving greenhouse gas levels that rise and fall with cold and warmth. Ocean sediments preserve chemical fingerprints, especially in the shells of tiny organisms that lived and died in waters that were warmer or colder depending on how much ice existed on land. On continents, the land itself bears the marks. Valleys carved too wide for their rivers, ridges of rock left like scars at the edges of former ice, boulders carried far from their birthplace and dropped where the ice finally gave up its grip. When those records are lined up, the rhythm is unmistakable. Long glacial buildups, shorter warm intervals, repeating with enough regularity that it feels almost like a rule the planet follows. And yet even inside that repeating rhythm, there's a deeper puzzle waiting. The strongest, most direct seasonal changes in sunlight are tied closely to the cycles of tilt and wobble tens of thousands of years, not 100,000. And still, the late Ice Age world seems so often dominated by that longer beat. The orbit's shape acts like an amplifier, yes, but the climate's response is more than simple amplification. It's as if the system learned a new way to behave. That question, how Earth shifted from a 40,000-year world into a 100,000-year world, leads into thresholds: ice sheet stability, ocean memory, and the way feedbacks can lock a planet into longer moods once certain conditions are met. The orbit provides the timing, but the climate chooses how to answer, and Earth's answers have not always been the same. Around 1 million years ago, Earth changed its tempo. For a long stretch before that, the planet's glacial rhythm was clearer, almost cleaner. Ice waxed and waned on a cycle that matched the slow swing of Earth's tilt about 41,000 years. The tilt would shift, high-latitude summers would strengthen or weaken, and the ice would respond in a way that seems, at least from the distance of ice cores and seafloor sediments, relatively straightforward. The system still had complexity, still had feedbacks and regional variations, but the pacing made sense. The strongest seasonal lever lined up with the dominant cycle in the record. Then the pattern stretched. The ice ages became longer, deeper, more stubborn. Instead of returning to warmth every 40,000 years, the planet began lingering in glacial conditions for close to 100,000 years at a time, with warmer intervals arriving less often and sometimes ending more abruptly. The signatures in marine sediments grew larger. Sea level swings became more dramatic. The ice volumes implied by isotopes became heavier, like the planet was holding more water on land and refusing to let it go. The strange part is that the orbital cycles didn't change. Earth didn't suddenly invent a new tilt period. Precession didn't stop wobbling on its old schedule. The eccentricity cycle, the slow stretching and rounding of the orbit, had always been there. And yet, the climate began to behave as if the long eccentricity rhythm had become the main drummer. This shift is sometimes called the Mid-Pleistocene Transition, and even the name sounds like what it is. A boundary, a turning point, not in a single event, but in a mode of behavior. It was less like a switch flipping, and more like a system gradually drifting toward a new set of rules, until, at some point, the new rules were what held. When you look at that transition closely, you start to see that the real question isn't, why did eccentricity become stronger? It's why did Earth become harder to melt? Because if ice sheets become large enough, thick enough, high enough, they stop responding easily to the shorter pulses of summer strength. They develop a kind of inertia and internal structure. They become less like seasonal snow and more like continental machinery. In that case, the 40,000-year tilt cycle might still modulate the sunlight, but the ice may no longer be sensitive enough to retreat fully every time tilt swings towards stronger summers. Instead, the ice persists through one tilt cycle, and another, accumulating more mass, altering the atmosphere more strongly, rearranging ocean circulation more completely, until only a particularly favorable alignment, amplified by eccentricity, can push the system over the threshold into a full deglaciation. That idea? Thresholds is a quiet key. Climate doesn't always respond smoothly. It can resist change for a long time and then, once pushed far enough, shift more quickly. Not because something magical happens, but because the system contains feedbacks that behave differently depending on state. A small nudge in one climate can be absorbed. The same nudge in another climate can be amplified. Earth can sit in a basin of stability, and then, slowly, the basin can shallow until it spills. During the transition to the longer cycles, several basins may have been shifting at once. One possibility is that the planet had been cooling gradually for a long time, over millions of years because of slow geological processes, changes in mountain building, in the long-term carbon cycle, in the background chemistry of oceans, in how easily ice could survive at high elevations. That gradual cooling would have made it easier for ice sheets to grow larger with each cycle. Larger ice sheets are not just bigger versions of smaller ones. They behave differently. They can develop broad plateaus where accumulation continues year after year. Their surfaces rise into colder air. Their edges can become pinned in certain regions by topography, allowing them to persist even when conditions begin to improve. As ice sheets grow, they also scrape and grind the land beneath them, turning rock into fine sediment. That matters because it changes how water flows and how the ice base behaves. Fine sediments can create slippery beds once meltwater appears, affecting how ice slides. Ice dynamics. How a sheet flows, whether it locks in place or surges, can determine whether the ice responds gradually or collapses more suddenly when warming finally arrives. Over long spans, an evolving landscape under the ice may have changed the character of the ice itself. Another possibility sits with the oceans, where time moves differently. The deep ocean can store cold and carbon for thousands of years. If ocean circulation became more stratified, less mixing between surface and depth, then carbon dioxide could be held in the deep ocean more effectively during glacial phases. That would lower atmospheric CO2 more, strengthening cooling, making ice more stable. And when CO2 is low, the planet is more sensitive to changes in sunlight because the greenhouse blanket is thinner. A slightly weaker summer becomes more consequential. A slightly stronger summer might still not be enough to melt the ice because the baseline is colder and the ice is higher. In that kind of world, a warm phase produced by tilt alone might not fully break the glacial state. It might warm the margins. It might cause a partial retreat. But the system would settle back into cold because the ocean would keep carbon locked away and the ice would keep reflecting sunlight. Only when orbital alignment produced unusually strong northern summer insulation, strong enough, sustained enough, would the ocean begin releasing more carbon. The greenhouse effect would strengthen, and the retreat would become self-reinforcing. Dust may have played its own part too, not as a simple villain or hero, but as a messenger between land, air, and sea. Glacial climates tend to be drier and windier. Sea level drops expose shelves and broad plains. Vegetation thins, soils loosen, and winds carry more dust. That dust can cool the planet by scattering sunlight in the atmosphere. But it can also fertilize the oceans, feeding microscopic life that draws carbon from the surface waters and helps push it into the deep. More dust could mean a stronger biological pump, more carbon stored in the ocean, lower CO2 in the air, and deeper cold on land. At the same time, dust settling on ice can darken it and enhance melting locally. The net effect depends on location, season, particle type, and the state of the system. But as part of a shifting glacial regime, dust could have strengthened the planet's ability to hold on to cold. All of these ideas have one shared theme. The climate system may have become more tightly locked, more internally reinforced, more reluctant to switch states. In that case, the 100,000-year rhythm is less about eccentricity forcing ice ages directly, and more about eccentricity determining when the strongest combination of orbital conditions occurs, the moments when the system can finally be pried out of deep glaciation. That framing also matches what the record seems to show. The build into a glacial state is often slow, taking tens of thousands of years. The return to warmth can be faster still slow on human terms, but quicker in the context of the cycle. It's as if the planet drifts into cold gradually, stacking its sheets of paper one by one. And then, when enough factors align, it moves into a different set of feedbacks and releases. A full deglaciation is not simply more sun, less ice. It's a cascade. Stronger northern summers begin melting the margins. Meltwater appears. Snow lines rise. Darker ground and darker ocean water are exposed, absorbing more heat. Sea ice retreats, allowing the ocean to release more warmth into the air. Ocean circulation shifts. Carbon dioxide begins to rise as the ocean warms and ventilation changes, and that CO2 rise amplifies warming. Vegetation shifts northward, changing albedo again. Ice dynamics can accelerate retreat, especially if meltwater reaches the base and lubricates the sheet, or if marine-based parts of the ice become unstable. What looks like a rapid end in the record is still thousands of years long, but it carries the feeling of a tipping point because several reinforcing loops begin to push in the same direction at once. And then, eventually, the planet settles into a warm interval, an interglacial, where ice is mostly confined to Greenland, Antarctica, and high mountains, and sea level stabilizes at a higher stand. The ocean breathes differently. The atmosphere holds more CO2. The seasonal patterns shift again, and for a while, the system rests in a different basin, until it starts to drift back. It's worth pausing here and letting the scales sink in because it's easy to make these cycles sound tidy. They aren't. They're consistent enough to recognize, but each one has its own personality. Some interglacials last longer than others. Some deglaciations appear more abrupt. Some glacial buildups include smaller warm pulses inside them. The climate system is not a perfect clock. It's a complex body responding to slow external pacing and internal feedbacks. Still, the repeating structure is strong. Weak northern summers invite ice. Ice invites more cooling. Oceans and greenhouse gases tend to reinforce the direction. The system becomes sticky. When the alignment reverses strongly enough, warming begins, and once warming crosses certain thresholds, it accelerates. This is why, when people ask, what starts an ice age? The best answer is rarely a single cause. It's a set of conditions that slowly becomes favorable. Summers that lose some of their melt power, snow that survives, reflective surfaces that expand, CO2 that drifts downward, oceans that rearrange heat transport. None of these are dramatic alone. Together, over long spans, they reshape the world. And it's also why, when people ask, what ends an ice age? The answer is again a combination. Enough summer sunlight returns to begin consistent melting, and then the feedbacks flip dark surfaces absorb more heat, oceans release carbon, greenhouse warming strengthens, and the retreat becomes its own momentum. In the last part of this story, what feels like the final layer is also one of the most quietly powerful, the role of greenhouse gases, especially carbon dioxide, not as the original trigger, but as the amplifier and the memory. The orbital cycles are the pacing, but greenhouse gases can deepen the cold and heighten the warmth, stretching the planet's moods into longer, more decisive states. Because Earth doesn't just change how much sunlight arrives, it changes how much warmth it keeps. And that difference between receiving energy and holding on to it is where the long rhythm becomes a true transformation. Carbon dioxide doesn't feel like weather. You can't hear it, you can't see it in the air the way you see fog, and you don't sense it the way you sense a drop in temperature when you step into shade. And yet, over long spans of time, it behaves like one of the planet's quiet levers, never the first hand to move, but often the hand that makes the movement matter. In the long glacial rhythm, the orbital cycles set the timing. They rearrange sunlight season by season, century by century. They decide when high-latitude summers grow weaker or stronger. But the climate's response to that rearrangement is amplified and deepened by the gases in the atmosphere, especially carbon dioxide. Not because CO2 creates the rhythm by itself, but because once the planet begins drifting in one direction toward cooling or toward warming, CO2 tends to follow in a way that reinforces the drift. It's less like a spark and more like a bellows. It doesn't light the fire, but it can make it burn hotter or let it fade into embers. To understand why carbon dioxide behaves that way, the first thing to remember is that the atmosphere is not the main storage vault for carbon. The ocean is. The sea holds vastly more carbon than the air does, dissolved and stored in different forms throughout its depth. That means small changes in how the ocean circulates, how warm it is, how much mixing happens between surface and deep layers. Those changes can move carbon back and forth between ocean and atmosphere on timescales of centuries to millennia. And those timescales, slow as they are, match the tempo of ice ages far better than a human lifetime ever could. When the planet begins to cool, when northern summers weaken and ice begins to spread, the surface ocean also cools, especially in high latitudes. Colder water can hold more dissolved carbon dioxide. So over time, the ocean draws CO2 out of the atmosphere and keeps it. That drawdown doesn't happen overnight. It unfolds gradually as ocean waters absorb gas and as circulation patterns carry carbon into deeper reservoirs. But as the atmosphere loses CO2, the greenhouse effect weakens slightly. Less heat is trapped. Cooling becomes easier to sustain. Ice becomes harder to melt. The direction the planet started moving, inset by sunlight distribution, gets a supportive push from the carbon cycle. And there's more than one way the ocean stores carbon. Some of it is simple chemistry, gas dissolving into cold water. Some of it is biological. Microscopic life in the surface ocean takes up carbon, builds organic material, and in some cases builds shells. When those organisms die, some fraction of their carbon sinks. Over long periods, that sinking acts like a conveyor moving carbon away from the surface and into deeper water and sediments. The efficiency of that biological pump depends on nutrients, winds, temperature, and circulation. Glacial climates can change all of these, sometimes increasing dust-borne nutrients like iron, sometimes altering upwelling, sometimes reorganizing food webs in ways that change how much carbon the ocean stores at depth. So CO2 is not just passively absorbed. It's cycled, processed, buried, and preserved by the ocean as the climate shifts. On land, the carbon story is tangled in its own way. As ice advances, it scrapes away forests and soils in the places it covers. That destroys local carbon stores. But at the same time, colder temperatures can slow decomposition in places that remain ice-free, allowing organic matter to accumulate in soils. Permafrost expands, locking carbon away. Wetlands shrink in some regions and expand in others, changing methane as well as carbon dioxide. Vegetation shifts across continents, and each shift changes how much sunlight the land absorbs and how much carbon the biosphere can exchange with the air. None of these land processes are simple enough to summarize as plants take up CO2 or plants release CO2. They are state-dependent, region-dependent, and time-dependent. The big stabilizing force over the glacial rhythm is still the ocean. But the land adds texture and complexity, local pulses, regional contrasts, and additional feedbacks that can matter when the system is near a threshold. What we do know, with unusual clarity for deep time, is what the ice itself tells us. Ice cores preserve bubbles of ancient air. Those bubbles show that during glacial periods, atmospheric CO2 tends to be lower, and during interglacials, it tends to be higher. The numbers are not astronomical by modern standards, but the climate effect is large. A shift that looks modest on paper can produce meaningful changes in global temperature, especially when it combines with reflective ice, altered ocean currents, and changes in water vapor and clouds. Carbon dioxide in this context is like a volume control on the planet's response. It helps determine how deep the cold can become and how fully warmth can return. And because CO2 moves slowly, it also acts like a kind of memory. The orbit can shift the sunlight pattern toward warming. But if the ocean is still holding on to cold conditions and still storing carbon at depth, the atmosphere doesn't immediately jump to a warmer state. It takes time for the ocean to warm. It takes time for circulation to adjust. It takes time for CO2 to rise and for the greenhouse effect to strengthen. That lag can help explain why deglaciation often feels like a release that happens after the system has been pushed for a while, like a door that won't open until the hinges finally move. When warming does begin in earnest, CO2 tends to rise again, not as the first domino, but as one of the most important ones in the chain. As the planet warms, the ocean surface warms too. Warmer water holds less dissolved carbon dioxide, so it begins to release CO2 back into the air. At the same time, changes in wind patterns and ocean circulation can ventilate deep waters that had been isolated, bringing carbon-rich water to the surface. That carbon escapes into the atmosphere. CO2 rises, the greenhouse effect strengthens, warming becomes easier to sustain. Ice retreats further, exposing darker land and darker ocean, which absorb more heat, which warms the ocean more, which releases more CO2. The feedback flips direction, and the system begins to reinforce warmth instead of cold. Methane and nitrous oxide also move with these cycles, responding to wetlands, temperature, and biological processes. Methane tends to be lower during glacial periods. When wetlands shrink and the world is drier and colder, it rises during interglacials. Nitrous oxide shifts as well. But CO2 is the heavy mover in this story, the slow, persistent greenhouse influence that aligns with ice volume and global temperature in a way that shows up clearly in the record. So when we talk about orbital cycles initiating change and greenhouse gases amplifying it, we're describing a partnership across time. Orbital geometry nudges. The carbon cycle answers. The answer can deepen into a new climate state. But the carbon story is incomplete if we leave out the oceans as heat engines, not just carbon reservoirs. Because ice ages are not only about how much sunlight arrives, they are about where heat is moved. The ocean is the planet's great transport system for warmth. Currents move heat from the tropics toward the poles. They carry warm surface water northward, where it cools and sinks, forming deep water that flows back through the abyss. This circulation is not a single stream, but a pattern of flows shaped by temperature, salinity, winds, and the arrangement of continents. During a glacial buildup, when ice spreads and high latitudes cool, the patterns of deep water formation can change. Surface waters can become fresher from increased snowfall, or from meltwater pulses during unstable phases. Fresher water is less dense, and that density matters because sinking requires density. If sinking slows or shifts, the whole heat conveyor can weaken or reorganize. Less heat transported northward can intensify high-latitude cooling. That makes summers less effective, making ice more stable. It's another reinforcement loop. Cooling changes circulation. Circulation changes heat transport. Heat transport changes cooling. This is one reason the ocean can make the climate feel sticky. Once circulation reorganizes into a glacial mode, it can hold the system in place, keeping carbon stored at depth and limiting warm water delivery to the regions where ice is most sensitive. Sea ice adds a further layer. When sea ice expands, it acts like a lid on the ocean surface. It reduces the transfer of heat from the ocean to the atmosphere. It also brightens the surface, reflecting sunlight. Both effects support cooling. When sea ice retreats during warming, the dark ocean surface reappears, absorbs sunlight, and releases stored heat into the air. That accelerates warming. Sea ice, unlike continental ice sheets, responds more quickly, and in doing so, it can help the larger system shift pace at key moments. And then there is sea level, the long, slow rise and fall of the shoreline. As ice sheets grow, sea level drops. When sea level drops, shallow seas narrow or vanish. Straits close. Continental shelves become land. These geographic changes can alter ocean circulation by blocking pathways or opening new ones. They can change how salt and heat are exchanged between basins. The ocean's geometry shifts, and the ocean's behavior shifts with it. When ice melts, sea level rises again. The ocean spreads across shelves, reconnecting basins, reopening pathways. Circulation can strengthen or redirect. The distribution of heat changes. Warming can accelerate. So the ocean is not just responding, it is participating. It is part of what makes a glacial period long, and part of what makes a deglaciation eventually decisive. If you step back far enough, you can see why the planet's climate cycles are not neat, symmetric waves. They are shaped by lags and thresholds, by systems that store heat and carbon and release them slowly, and by ice that grows gradually, but can retreat more quickly once the balance tips. A full thaw is not a simple reversal of the freeze. It's a transformation that spreads through the system. First, the edges of ice begin to fail under stronger summers. Meltwater appears. The albedo changes locally. The atmosphere warms a little. Sea ice retreats. The ocean absorbs more sunlight. Circulation shifts. Carbon dioxide rises. The greenhouse blanket thickens. The warming becomes more robust. Ice sheets thin and shrink, exposing more dark surface, which absorbs more heat. The retreat builds momentum. But even then, the path is uneven. Meltwater can disrupt circulation in ways that create temporary coolings or regional reversals. Some parts of an ice sheet can collapse faster than others depending on whether the ice is grounded below sea level, whether it is lubricated at its base, whether it is buttressed by floating ice shelves. Deglaciation can include pulses episodes where the system lurches forward, then pauses, then surges again. In the end, the planet arrives at an interglacial state. Less continental ice, higher sea level, warmer oceans, higher greenhouse gas concentrations than in the glacial depths. The climate becomes, for a time, less dominated by ice albedo feedback and more dominated by the familiar patterns of ocean-atmosphere exchange we recognize today. And it's easy, living inside an interglacial, to mistake that state for the planet's default. But it isn't. It's one mode among others. A basin the system rests in for a while before drifting again. Which brings us to the uncomfortable, fascinating question that always waits at the edge of this story. what happens next? On geological schedules, the orbital cycles continue. The tilt keeps swinging. The axis keeps its slow wobble. The orbit keeps changing shape. Those motions will keep rearranging sunlight no matter what else happens on Earth. They will eventually create configurations that, in the past, were favorable for glacial inception cooler northern summers, snow that lingers, ice that begins to stack. But the climate system does not respond to orbital forcing in isolation. It responds through its current state, through the warmth stored in the oceans, through the concentration of greenhouse gases in the atmosphere, through the conditions of ice sheets that exist now, and through the feedbacks those conditions enable or suppress. If greenhouse gases remain high, the threshold for ice growth shifts. Summers that might once have allowed snow to survive may now melt it away. The feedback that normally amplifies cooling may fail to engage. The system may be nudged toward glaciation by orbital geometry and yet remain in a warm basin because the greenhouse blanket and ocean heat content keep the surface from crossing the critical line where snow persists. That doesn't erase the long rhythm, it complicates it. It delays it. It changes the conditions under which the old pattern can reassert itself. Earth has always been a planet of slow forcing and layered responses. What feels new is the speed at which the atmosphere's composition has shifted in the modern era, fast enough that the climate system, with its long oceanic memory, is being pushed in ways it cannot instantly absorb. Still, the long view matters, because over tens of thousands of years, the orbit will keep moving, and the climate will keep searching for its next stable state. Whether the next deep freeze arrives on the old schedule or later, whether it begins softly with lingering snow or is postponed until a more extreme orbital alignment, the same basic physical logic remains. Ice grows when summers cannot erase winter, and ice retreats when summers regain enough strength and the feedbacks swing toward warmth. And beneath all of it, the oceans keep time in their depths holding heat, moving it, storing carbon, releasing it, ensuring that whatever changes come, they will come with patience. The planet is not in a hurry. And that, in a strange way, is what makes the long rhythm both so unsettling and so beautiful. It doesn't need drama to reshape the world. It only needs time. If you stand far enough back from the details, far enough that continents feel like shapes in a dim atlas and centuries feel like seconds, you start to see how many of Earth's biggest transformations are built from the smallest insistences. A little less summer melt, a little more snow left behind, a little more brightness on the surface, a little less heat absorbed, a little more cold that carries into the next season. That's the quiet architecture of glaciation. And it's also the quiet architecture of the world we live on. Because the planet we recognize is not simply Earth as it is. It's Earth as it happens to be in a warm interval, after the last great retreat of ice, still carrying the fingerprints of that retreat in the shape of its valleys and coastlines. The landscape holds memory, not in a sentimental way, but in a physical one. It holds memory the way a shoreline holds memory of higher water, the way a tree trunk holds memory of drought in narrow rings. During glacial maxima, sea level is lower. Vast shelves are exposed. Places that are ocean today become plains and corridors. Rivers run differently because the base level they drain toward the sea has shifted. Wind patterns change because the temperature gradient between the poles and tropics grows sharper. Dust travels farther. Deserts expand in some regions and contract in others. Life rearranges itself, not quickly but faithfully, following the moving boundary lines of temperature and moisture. Then, during the long thaw, the process reverses, but never perfectly, never smoothly. Sea level rises, flooding the shelves again. Coastlines retreat inward. Estuaries form where river valleys drown. New marine habitats appear. Old land routes vanish. The rebound of land formerly pressed down by ice continues for thousands of years, slowly lifting coastlines even as sea level rises, creating strange local contradictions. Places where the sea seems to retreat because the land is rising, and places where the sea advances because the land is still heavy with the after effects of ice. Even in the modern world, you can find these mismatched motions. They're not always obvious, but they're there. Ancient shorelines perched above current ones, terraces cut into hillsides, beaches that now sit inland as if abandoned by the sea. Glacial cycles don't just change climate, they change geography. And geography changes climate back. When sea level drops, shallow seas narrow, straits become land, and the exchange of water between basins can weaken. When sea level rises, those pathways reopen, and currents regain routes they lost. The ocean's plumbing matters, because the ocean is the planet's heat-moving system. Alter the plumbing, and you alter where warmth goes, where cold collects, how moisture is delivered, and how the atmosphere behaves above it. In other words, the planet's long cycles are not just celestial. They are planetary in the fullest sense. Orbit and axis, yes, but also water and rock and living things all feeding back on one another. This is why the pace feels so unlike anything in daily life. We're used to causes that arrive with a timestamp. We're used to beginnings and endings we can name. But ice ages don't begin with a single winter that was too cold. They begin when the statistics of summers tilt. They begin when snow survives in the right places often enough that right place becomes right region, and right region becomes a continent learning a new habit. The end is similar. It doesn't start with a dramatic heat wave. It starts when summer sunlight returns just enough to make the survival of snow less reliable. A few summers begin to erase more than they used to. The bright surfaces shrink. Darker surfaces reappear. Heat absorption increases. The system quietly shifts its bias. And then, once the bias flips, the feedbacks change sides. What makes these transitions feel so powerful in the records is not simply that ice grows and melts. It's that the planet changes the rules of its own balance as it moves between states. In a cold world, ice and snow are everywhere, reflecting sunlight and keeping the system cool. In a warm world, darker oceans and forests absorb sunlight, making warmth easier to sustain. The same amount of incoming solar energy can produce very different outcomes depending on the planet's surface and atmospheric composition. In that way, an ice age is not just colder weather. It's a different configuration of Earth. The atmosphere carries less moisture. Deserts and dusty plains expand. The jet stream behaves differently. Storm tracks shift. The ocean circulation reorganizes. Greenhouse gases settle into lower ranges. Sea level drops. Ecosystems migrate. Some species become isolated into refuges. Others expand across the new open corridors. Human populations, in our own recent evolutionary story, faced a world where coastlines were far out from today's shores, where some islands were part of continents, where mountain passes were colder, where travel routes depended on the presence or absence of ice. And when the thaw comes, it isn't a simple return. It is a rebuilding. Rivers carve new paths, lakes form and drain, soils develop on fresh deposits of glacial sediment, forests advance into land that was once too cold for trees to survive. The atmosphere grows wetter. Weather becomes, in many places, less extreme than during glacial peaks, though still shaped by lingering ice and by oceans that are adjusting to new coastlines. That rebuilding is one reason interglacial periods can feel so stable from the inside. The planet is not actively rearranging itself as violently as during full glaciation, but stable is relative. On glacial time, even stability is a phase. When people ask whether the next ice age is due, they're often imagining the glacial rhythm as a strict calendar. But Earth's cycles aren't obligations, they are tendencies. The orbital cycles set the pacing, but the climate system can follow that pacing in different ways depending on thresholds and background conditions. Even in the distant past, the system sometimes hesitated. Sometimes it warmed less than expected. Sometimes it didn't fully deglaciate. Sometimes it lingered in intermediate states. The rhythm remained, but the expression varied. That variability is part of what makes paleoclimate such a living science rather than a completed story. The planet follows rules, but those rules play out through complex feedbacks that can produce different outcomes depending on starting conditions. In the present era, The starting conditions are unusually shifted. The atmosphere contains more greenhouse gas than it typically did during comparable points in previous interglacials. The oceans have absorbed large amounts of heat. The cryosphere ice in all its forms is responding not as a single uniform sheet, but as a set of interconnected systems. Sea ice, mountain glaciers, Greenland, Antarctica, permafrost, seasonal snow cover. Each responds differently, with different time lags and different thresholds. So the question, when is the next ice age, becomes less like reading a calendar and more like asking when a complex system will cross a particular line. In the classic orbital picture, glacial inception tends to begin when northern high-latitude summers become weak enough that snow can persist. That requires a particular configuration, generally reduced summer insolation in the north, sustained long enough, with feedbacks that reinforce the initial cooling. In previous eras, that cooling would be supported by declining CO2 as oceans cooled and absorbed carbon, by expanding snow and ice reflection, and by circulation patterns that reduce heat delivery to key regions. But if CO2 remains elevated, the climate may not cool enough for that first persistent snow to take hold. The gatekeeper summer may still do its job too well. Snow may fall and then melt. Even if summers weaken slightly under orbital change, the baseline warmth may remain above the threshold that matters. That's the core of the delay idea. Not that the orbit stops cycling, but that the climate system doesn't cross the snow survives threshold when it otherwise might. Over very long timescales, though, the orbit will continue to shift. Eccentricity will increase again, amplifying the seasonal effect of precession. Tilt will pass through lower phases, reducing summer intensity at high latitudes. There will be periods, thousands of years from now, where the geometry lines up in ways that, historically, were strongly favorable for ice growth. If greenhouse gas levels were to fall back toward pre-industrial ranges long before then, the system would become more capable of responding in its old pattern. Even if greenhouse gases remain higher than the old baseline, extreme orbital alignments could eventually provide enough reduction in summer melt, especially if the planet's feedbacks have shifted by then due to changes in ice sheets and ocean circulation. The system might find a new pathway into glaciation, perhaps different in details but similar in the underlying logic. Persistent snow, growing reflectivity, cooling oceans, shifting carbon, and a slow lock-in of cold. Because the rhythm is resilient, not because it is inevitable on a schedule, but because it is rooted in geometry and energy balance. Earth will always receive sunlight. Earth will always radiate heat to space. The balance will always depend on how energy is distributed across seasons and latitudes and how the planet's surface and atmosphere respond. The long cycles are the dance between incoming light and outgoing heat, mediated by oceans and ice. There's another aspect of this story that can feel almost philosophical. The way the planet's greatest changes can occur without anything feeling different at the time. Imagine living in a world where each summer is a fraction cooler than the last, but not enough for anyone to call it unusual. Imagine that change continuing so slowly that no one ever points to a year and says, "This is when the Ice Age began." The landscape shifts anyway. The forest line creeps. The snow patches persist. The ice thickens in the high places. Centuries later, a valley that once held summer grass becomes a corridor of ice. Thousands of years later, a continent is crowned with a sheet that changes winds and storms and sea level. Now imagine the opposite, living through the thaw. Each summer melts slightly more than the last. Streams run a little stronger. Lakes grow in basins at the ice edge. The coastline creeps inland so slowly you'd need many generations of maps to notice. The atmosphere grows a bit wetter. Forests advance. And yet no one says, "This is the moment the Ice Age ended." It's only in the long look back that the shift becomes obvious. That's the nature of deep time. It doesn't announce itself. It accumulates. The reason Earth's glacial rhythm matters is not just because it's fascinating in its own right. It matters because it shows how sensitive the climate system is to small, persistent changes. How feedbacks can amplify what begins as a faint orbital nudge into a world-altering transformation. It shows how the planet's components are intertwined, The orbit setting the pacing, the ice changing the surface, the oceans moving heat and carbon, the atmosphere responding in composition and circulation, life rearranging itself across continents. And it leaves us with a final kind of awareness, one that sits quietly behind the science. The climate we experience is not a fixed background. It is a state the planet occupies for a while. We are living in a warm interlude. It has lasted long enough to feel normal, long enough to build stories and calendars and borders and expectations, but in the planet's longer memory, warmth and cold are both temporary basins. The system drifts between them under slow celestial timing and slow internal feedback. If you listen carefully to Earth's past, you can hear that drift, not as a warning siren, not as a prediction stamped with a date, but as a reminder of scale and patience. That the most powerful forces shaping the world are often the ones that move so slowly we can't feel them move at all. And that, perhaps, is the most haunting part of the long rhythm, how gentle the first step is, and how vast the destination can become. There's a moment in this story where the planet stops feeling like a place and starts feeling like a process. Because once you accept that ice ages are not rare accidents but recurring states, you begin to see Earth less as a stage and more as a system one that is always balancing energy, always redistributing heat, always negotiating between sunlight and reflection, between ocean storage and atmospheric loss. The world we walk through becomes a snapshot of that negotiation, taken mid-sentence, and the sentence is long. To keep following it, it helps to look more closely at something that sounds simple but isn't. How a small change becomes a continental outcome. If northern high-latitude summers receive slightly less energy for long enough, snow persists. That is the seed. But a seed doesn't become a forest without conditions. It becomes a forest because the environment shifts in ways that protect it. The same is true for ice. When snow begins surviving through summer, it doesn't merely add a bit of whiteness to the map. It changes the environment in ways that make survival easier next time. The surface brightens, reflectivity increases, temperatures drop. But there's another detail that matters just as much. The snow that survives is not the same material it started as. Fresh snow is airy. It has space between crystals. It traps air. It's light. Over time, under the pressure of new snowfall and its own weight, it compacts into firn-dense, granular, older snow. Firn is a transitional state, and it's important because it marks the point where the winter's gift becomes something that can endure. Firn gradually becomes ice. The trapped air pockets shrink. The structure becomes harder, heavier, and far more resistant to being erased by a single warm season. This is the chemistry of patience. It's not just cold, it's persistence that turns snow into something that reshapes continents. Once an ice mass becomes large enough, its edges begin to flow outward under gravity. Glacial ice moves, not quickly in the way a river moves, but constantly. It creeps, deforms, slides. It carries rock embedded within it. It grinds the ground beneath. It scours and scrapes and rearranges. So the growth of ice is not simply vertical, stacking layer upon layer. It's also horizontal. It spreads. And as it spreads, it becomes a climate feature large enough to influence the sky above it. This is one of those feedbacks that can feel almost unsettling. The ice doesn't just respond to the climate. It begins to dictate parts of it. A continental ice sheet is like a cold plateau, changing pressure gradients and steering winds. It can shape where storms travel and where snowfall accumulates, effectively helping to feed itself in some regions while starving others. At the same time, the expanding ice sheet begins to change what the planet looks like to the sun. Not in a visual sense, but in an energy sense. Brightness changes the energy budget. When the surface reflects more sunlight, less energy is available to warm air and ground. That means the entire system operates at a slightly lower temperature. And that lower temperature shifts other processes as well. Moisture, clouds, vegetation, ocean exchange. Moisture is one of the more subtle threads here. Cold air holds less water vapor. In a colder world, the atmosphere can become drier overall, even while ice grows. That sounds contradictory until you remember that ice sheets don't require endless snowfall everywhere. They require enough snowfall in the right accumulation zones, combined with summers that don't erase it. A glacial climate can be drier in many mid-latitude regions while still producing thick ice in the north. In fact, the dryness can contribute to dustiness, and dust can interact with the ocean and carbon cycle, which can contribute to lower CO2, which contributes to cooling. So the system has these strange balances. Less moisture in the air can mean less snowfall in some places, but it can also mean less cloud cover in others, changing sunlight reaching the surface, changing temperature gradients, changing winds. There isn't one simple direction. There are regional mosaics with cold deserts in one area and snowfall engines in another. This is why the phrase ice age can be misleading. It suggests a uniform world of snow everywhere, a planet sealed under frost. In reality, a glacial world is a patchwork. There are vast ice sheets, yes. There are also permafrost regions, steppe landscapes, cold deserts, forests and refuges, and coastlines pushed far outward. There are places that are brutally cold and places that are simply dry. The planet does not cool evenly. It reorganizes. And because it reorganizes, it leaves behind clues that are not just in temperature records, but in patterns of life. Pollen preserved in lake sediments tells us where forests retreated and where grasslands expanded. Fossils show animals shifting ranges, some moving south, some moving into lower elevations, some adapting to cold open landscapes. Genetic patterns in modern species hint at past refugees, pockets where populations survived glacial extremes and later expanded when warmth returned. Even the distribution of certain soils and landforms, loess deposits from wind-blown dust, kettle lakes left by stranded blocks of ice, outwash plains built by meltwater rivers, tells a story of cold climates that were never simply winter all the time, but complex climates that rearranged water and wind. The more you look, the more you realize the planet has been through these rearrangements repeatedly, and that each time it does, it writes a new draft of the landscape. So when the system shifts toward deglaciation, the reversal is not simply ice shrinking. It is an entire planetary reconfiguration unfolding in the opposite direction with its own feedbacks and unevenness. As summers strengthen in key northern latitudes, melting begins along the margins. Meltwater appears not only at the surface but sometimes at the base, where it can lubricate the ice sheet bed and speed up flow. Ice that once crept outward steadily can begin to move faster toward lower elevations, where it melts even more readily. Portions of the ice sheet that are grounded below sea level can become unstable if warming oceans undermine their edges, creating potential for faster retreats in some sectors than in others. Meanwhile, as the surface darkens bare ground, open water, expanding forests, more sunlight is absorbed. This increases local warming and can push the melting boundary farther inward. Sea ice retreats, exposing dark ocean that absorbs sunlight and releases heat to the air, accelerating warming especially in autumn and winter. The atmosphere becomes wetter. Storm tracks shift again, often bringing more precipitation, but not always as snow. And through all of it, the oceans begin changing their carbon behavior. Warming waters release CO2. Changing circulation can ventilate deep waters and bring stored carbon back to the surface. CO2 rises, amplifying warming. Methane tends to rise as wetlands expand. These gases thicken the greenhouse effect, helping the planet climb out of glacial cold. The feedbacks switch sides. The system begins to favor warmth. It's important to recognize that the end of an ice age is not a single threshold, but a series of thresholds crossed one by one. A little more summer melt, then enough melt to lower albedo significantly, then enough warming to shift sea ice behavior, then enough ocean response to raise greenhouse gases, then enough ice retreat to raise sea level, altering coastlines and currents, then enough ecological change to shift land surface properties further. In that sense, a deglaciation is not a simple thaw. It's a chain reaction, slow at first, then more confident as feedbacks align. And in the geological record, Those deglaciations often appear faster than the glacials that preceded them. Not because they happen quickly in human terms, thousands of years is still an expanse we can hardly imagine, but because the buildup can take so long, and the release, once it begins, has more reinforcing pushes in the same direction. This asymmetry is one reason the glacial cycles have such a recognizable shape: a long descent into cold, and a more abrupt climb back toward warmth. Now, if we bring the lens back to the present, we stand in an interglacial that has been stable enough to feel like a baseline. The last major deglaciation reshaped coastlines, raised seas, and set up the climate patterns that allowed agriculture to spread and societies to settle. The Holocene has been, by glacial standards, gentle, not uniform. There have been fluctuations, droughts, cooler intervals, warmer intervals, but comparatively stable in its broad structure. From a deep time perspective, that stability is not a guarantee. It's a phase. The orbital cycles will continue. Eventually, the geometry will shift toward weaker northern summers again. Historically, that would set the stage for the next slow buildup. But as we've said, the climate's willingness to follow the old rhythm depends on thresholds, and thresholds depend on greenhouse gases, ocean heat content, and the state of ice and ecosystems. That creates a strange double awareness. On one hand, the orbital pacing is reliable. The tilt will swing. The wobble will continue. Eccentricity will rise and fall. The astronomical metronome does not stop. On the other hand, the planet's response is not a simple replay. The climate system is being pushed into conditions that are unusual relative to recent interglacials. That means the next chapters may not match the last ones exactly, even if the underlying physics remains the same. The system could delay glaciation. It could move into new intermediate states. It could respond differently because of altered boundary conditions, warmer oceans, different ice sheet configurations, changed ecosystems. Yet the ancient logic remains. Ice grows when summer can't erase winter, and it retreats when summer regains enough strength and the feedbacks swing warm. If you keep that logic steady, the long story becomes clearer, even when the details are uncertain. Because ultimately, this rhythm is not a mystery of caprice. It's a mystery of scale. It's what happens when geometry and feedbacks play out over time spans long enough for small nudges to become landscapes, and for landscapes to become climate. And maybe that is what makes the glacial rhythm feel so unlike anything else we know. It is the planet demonstrating again and again that patience is a force. When you realize that patience can be a force, you start to notice it everywhere in Earth's long story. Rivers carve canyons one grain at a time. Mountains rise by millimeters, then crumble and rise again. Coastlines shift without ever making a sound loud enough to be called an event. And ice is patience made visible. It doesn't need to hurry. It only needs the world to keep giving it small advantages long enough for those advantages to become irreversible. But there's another layer to the glacial rhythm that's easy to overlook, because it doesn't live in the ice itself. It lives in the way the planet keeps time. The orbit and axis cycles are predictable, but the climate response is not a simple mirror of them. It's delayed, filtered, and sometimes reorganized by the slowest parts of the system. That's why the record isn't a perfect sine wave. It's why there are long, cold buildups, abrupt warmings, pauses, reversals, and smaller pulses embedded within the bigger swings. In deep time, the climate behaves less like a clock and more like a body. It has inertia. It resists sudden shifts. And then, when the right thresholds are crossed, it can change quickly compared to its usual pace. Those thresholds are not single lines on a diagram. They're places where multiple processes meet. One threshold might be the point at which snow survives summer consistently in a broad enough region that it stops being a local curiosity and becomes a regional feature. Another might be the point at which sea ice expands far enough that it begins to significantly reduce ocean-atmosphere heat exchange across an entire basin. Another might be the point at which ocean circulation shifts into a mode that stores carbon more efficiently at depth. Another might be the point at which an ice sheet grows high enough that its own elevation makes it resistant to melting even when summers strengthen. These thresholds don't always get crossed in the same order. They don't always get crossed at the same time. And when they do get crossed, they don't always lock the system in permanently. Sometimes the system drifts near a threshold and then backs away. Sometimes it crosses and then oscillates, searching for stability. This is why, when you look closely at glacial records, you see complexity layered on top of rhythm. You see warming events inside a glacial period, temporary relaxations where parts of the system briefly behave as if they want to thaw, then return to cold. You see regional differences, one ocean basin shifting circulation earlier than another, one hemisphere showing stronger seasonal changes, one continent responding more quickly because of geography and topography. You see the planet as a collection of linked subsystems, not a single uniform thermostat. And still, through all that complexity, the big pattern holds. A glacial world accumulates cold. An interglacial world accumulates warmth. The orbit paces the opportunity. The feedbacks decide whether the opportunity is taken. The longer you spend with this story, the more you begin to see that the phrase Ice Age can mean two different things. In casual conversation, it sounds like a singular era, an age of ice, one long frozen chapter. But in geology, Ice Age can also mean an extended period in Earth's history when permanent ice exists somewhere on the planet. By that definition, we are still in an ice age right now, because Antarctica and Greenland carry large, persistent ice. What we've been talking about are the pulses within that broader ice age, glacial periods and interglacials, the expansions and retreats of continental ice in the Northern Hemisphere. That distinction matters because it reminds you that Earth's climate has multiple nested rhythms. There are short-term variations on top of longer ones. There are cycles within cycles, and beneath them all are even slower trends changes in continental positions, mountain building, long-term carbon cycling through rock weathering and volcanism that set the background state in which glacial cycles play out. This is part of why the Mid-Pleistocene shift feels so important. It suggests that the background state of the planet can drift until the same orbital pacing produces a different kind of response. The metronome doesn't change, the dancer does. So what exactly does that tell us about the future? It tells us the future is not simply a rerun. It tells us that the orbital cycles will continue to offer windows where glaciation is favored. But whether the planet moves into glaciation during those windows depends on the background state, especially greenhouse gases and ocean heat. In the past, the background state was shaped by natural processes. Today, the background state includes a rapid addition of greenhouse gases to the atmosphere and a large, ongoing absorption of heat by the oceans. Those changes do not stop the orbital cycles, but they do change how the system responds to them. They effectively deepen the warm basin the climate is currently sitting in, making it harder for the system to climb out into a cold basin, at least for a while. And, for a while, in this story, can mean tens of thousands of years. That doesn't mean glaciation is gone forever. It means the threshold is moved. It means the orbit may present conditions that once would have been enough to begin ice growth, but now might not cross the line where snow persists. The system might hover near the edge and then drift back into warmth. It might wait for a more extreme alignment. It might require greenhouse gas levels to fall significantly before the old mechanisms can fully engage. If that sounds abstract, bring it back to the simplest condition again. Summer must fail to erase winter. In a warmer atmosphere, summer has a head start. Snow melts earlier, rain falls where snow used to fall. The snowpack is thinner going into the melt season. The land surface darkens sooner. All of those small shifts make it harder for persistent snowfields to survive. And if snowfields don't survive, the ice sheet doesn't get its foundation. The brightening feedback doesn't lock in. The slow stacking of paper doesn't begin. The entire glacial engine depends on that first persistent residue. Even so, the orbit continues to rearrange sunlight, and it can rearrange it strongly given enough eccentricity and the right precession alignment. There will be times, far ahead, when northern summers are considerably weaker than they are now. If the climate system is then in a state that allows snow to survive, if greenhouse gases are low enough, if ocean heat content is lower, if circulation patterns support cooling, then the ancient mechanism can wake again, and it will wake in the same quiet way it always has. Not with a dramatic freeze, but with summers that don't quite clean up. What's haunting about that is the way it redefines what beginning means. The beginning of an ice age is a statistical tilt and a slow persistence. It is something you only recognize with a long memory and careful measurement. In that sense, the Earth doesn't step into an ice age, it drifts into one. And that drift means the world has time to adjust. Sometimes enough time for life to migrate, adapt, diversify, or retreat into refuges. Sometimes not enough time for species that are specialized and slow to move. Glacial cycles have been engines of evolution and extinction alike. They create corridors and they close them. They isolate populations and then reconnect them. They shift ecosystems like pieces on a board. They have shaped the story of life, not as an occasional interruption, but as a recurring background rhythm. And they have shaped human history too, not only through obvious things like sea level and land bridges, but through subtler pressures. Aridity expanding in some regions, rainfall regimes shifting in others, coastlines moving, rivers changing, resources rearranging. The world in which humans spread and adapted was not static. It was a world whose climate lines were constantly sliding. That makes the Holocene feel even more unusual, and explains why its stability mattered so much. Agriculture depends on predictable seasons and reliable water. Permanent settlements depend on coastlines and rivers that do not move too quickly. The sense of a normal climate is, in part, a gift of living in a warm interval where the big ice sheets are not actively rewriting the map. But the deep time view doesn't allow us to treat that as guaranteed. It asks us to hold two truths at once. The climate system has repeated patterns, and the system can also shift its mode when background conditions change. This is where the long story stops being only about the past and becomes a way of seeing the present, because it shows how powerful small persistent changes can be. It shows how feedbacks can amplify a nudge into a new state. It shows how the ocean's slow memory can delay a shift and then, once released, help accelerate it. It shows how the planet's surface ice versus ocean versus forest versus grassland changes the energy balance in ways that reshape the atmosphere above. In other words, it shows that the climate is not a single dial, it is an interacting system with thresholds and momentum. And if you want a final image to hold, something simple enough to keep in the mind, it might be this. The Earth is always balancing a budget. Incoming sunlight is income. Outgoing heat is expense. Ice and clouds and surface brightness affect how much income is kept. Greenhouse gases affect how quickly expense can be paid. Oceans store savings and release them slowly. And the orbit decides how the income is distributed, who gets the strongest summer, who gets the weakest, and how that distribution shifts over millennia. Every glacial cycle is that budget drifting out of balance and then being pulled back slowly, imperfectly, and repeatedly. And the reason the story feels so quiet is because the planet doesn't need drama to do it. It needs only its steady celestial motions and the patience of feedbacks that never stop adding up. That's how continents learn to wear ice. That's how coastlines learn to move. That's how a world that feels fixed from the inside reveals itself over deep time as something that is always, always becoming. There's a certain kind of humility that settles in once you've spent time with these cycles. Not the performative kind, not the kind people wear like a badge, but the quiet kind that comes from realizing how much of the world we take for granted is actually the aftermath of changes we didn't witness. The ground under your feet, if you live in the northern half of the Northern Hemisphere, has probably been rearranged by ice. Not everywhere, not in the same way, but more often than most of us imagine. The soils that grow forests, the stones in fields, the gentle rolling hills that look natural and inevitable. Many of them are the signatures of glaciers that moved slowly enough to feel like stillness, and heavy enough to turn landscapes into something new. Even the idea of north carries glacial memory. During cold maxima, the north is not simply colder, It is different. It is a region of ice domes and winds that behave as if they have learned new routes. It is a region where rivers can be redirected, where lakes can appear and vanish, where coastlines can be far from where they are now. It is a region where the shape of the land is temporarily altered by weight pressed down under kilometers of ice. And then, when the ice finally releases it, lifted again in a rebound that continues long after the climate has warmed. This is one reason the glacial rhythm matters beyond the abstract. It isn't only a story of temperatures, it's a story of physical inheritance. When ice advances, it carries rock. It grinds rock into finer material. It deposits that material in belts and ridges that become future terrain. It leaves behind sands and clays and gravels and patterns that determine, thousands of years later, where wetlands form, where aquifers sit, where rivers cut channels, where fertile soil accumulates, where forests take hold, where agriculture thrives. It is almost unsettling to realize how much of human geography rests on glacial geology. Cities rise on river plains shaped by meltwater. Farmland spreads across sediment left by retreating ice. Water supplies depend on deposits that glaciers built and abandoned. A long vanished ice front can determine, in a quiet way, where people live and where they don't. And if you follow that thread long enough, you end up back where we began. The cycles are slow, but their consequences are intimate. So when we ask why Earth's climate keeps shifting between long freezes and shorter, warm intervals, we are not just asking an academic question. We're asking why the planet keeps rearranging its own living space, why it keeps rewriting the boundaries life has to adapt to, why it keeps changing the map. The answer, in its simplest form, is still the same. Orbital geometry changes the seasonal distribution of sunlight, and the climate system amplifies those changes through feedbacks. But the longer you sit with it, the more you realize that distribution is everything. Not total sunlight, not a dimming sun, but timing and location. The planet receives nearly the same yearly energy, yet by moving that energy around, strengthening one summer, weakening another, it can shift the entire system into a new state. That is the strange power of seasonality. Because what matters for glaciation is not the global average temperature in the abstract. It is whether a specific region, in a specific season, crosses a threshold often enough for long enough. Whether high-latitude northern summers are weak enough that snow remains. Whether that snow can persist, brighten the surface, and begin the long work of building ice. And once you see that, you begin to see why so much of the science focuses on a particular place and a particular time. Northern summer insolation at high latitudes. It's not that other regions don't matter. They do. The tropics store heat and drive circulation. The Southern Ocean mediates carbon exchange. The Antarctic ice sheet influences sea level and global albedo. But the switch that most reliably flips the glacial engine is northern summer melt. That's why the cycles can be paced by orbital mechanics without being perfectly regular. The orbit provides recurring opportunities for weak northern summers, but whether those weak summers create an ice age depends on what the rest of the system is doing. How much heat is stored in the ocean, where carbon is held, what the existing ice looks like, what vegetation covers the land, how dust is moving, how circulation patterns are arranged. It's a set of interlocked conditions. And in a set of interlocked conditions, timing matters. Sometimes the cycles align in a way that creates a strong push. Low tilt, a precession phase that places northern summer farther from the sun, and an eccentricity state that amplifies that distance effect. That combination can weaken northern summers enough to let ice begin, and once the ice begins, the feedbacks do the rest. Other times, the cycles don't align strongly enough. The summers weaken slightly, but not enough. Snow lingers in a few places, then vanishes. The system wobbles near the threshold and returns. That wobble itself is part of the story. Earth is not a machine that always reacts the same way. It is a system with memory and state dependence. And that means it can hesitate. It can be close to glaciation without committing. It can linger in intermediate conditions. It can move forward and backward across smaller thresholds before crossing the big one. This is also why the 100,000-year pacing is so intriguing. Eccentricity provides the slow modulation that determines when precession's seasonal timing is most powerful, but eccentricity alone is a weak direct forcing. So the dominance of the 100,000-year cycle suggests the climate system, at least in the last million years, behaves like a threshold system that requires the strongest combined push to exit deep glaciation. In other words, the climate can be paced by a weak cycle if it is waiting for the moment when all the other forces line up enough to break the ice's stability. The ice, once large, becomes stubborn. It becomes elevated. It becomes reflective. It becomes an atmospheric sculptor. It becomes a sea level lever. It becomes, in a sense, its own climate. And to end an ice age, you don't just need a little more sun. You need a coordinated shift. Stronger northern summers that can produce sustained net melting and feedbacks that flip from reinforcing cold to reinforcing warmth. Darker surfaces, rising greenhouse gases, shifting circulation, retreating sea ice, reorganizing storms. The system has to be nudged and then allowed to run downhill toward warmth. When you look at glacial terminations in the record, those transitions from deep cold to interglacial warmth, you see that downhill run. You see CO2 rising, you see temperature rising, you see ice volume dropping, you see sea level climbing, you see dust patterns shifting, you see the whole system shifting gears. And when you look at glacial inceptions, you see the opposite. A long, gradual climb into cold, with small changes accumulating, until the system is stable on the cold side. This difference in shape slow into cold, faster into warmth can be explained by feedbacks and inertia. Ice sheets take a long time to grow, but once melting begins across wide areas and feedbacks flip, retreat can accelerate. It is still slow by human standards, but faster than the buildup. So the glacial rhythm is not symmetrical. It's lopsided, like breathing. A long inhale, a shorter exhale. And if you hold that image, the planet breathing, you can also hold the next image that follows naturally. The atmosphere is breath. Because the air is not only temperature, it is composition. It is greenhouse gas concentration. It is dust load. It is water vapor. It is circulation. During glacials, the atmosphere tends to hold less CO2 and less methane. It tends to be drier. Dust tends to be higher. Those conditions are not separate from the cold. They help sustain it. They are part of the cold's architecture. During interglacials, greenhouse gases rise, dust often falls, moisture increases. Those conditions help sustain warmth. They are part of warmth's architecture. In this way, the planet's surface and its atmosphere are always co-authoring the state of the climate. The orbit sets the schedule of seasonal light. The Earth system writes the response. And what Earth has written, again and again, is a story where tiny differences, repeated long enough, become destiny, at least for a while, until the next repetition begins. Because that is the most persistent truth in the whole pattern. Even when the system pauses in warmth, it does not stop moving. The orbit continues. The axis continues its slow dance. The distribution of sunlight continues to shift. The ocean continues to store and release heat. The carbon cycle continues its slow exchanges. The planet keeps time. We live inside one beat of that timekeeping. We call it normal because it's what surrounds us. But Earth's long memory calls it a phase. And if you listen for the longer rhythm through the evidence in ice, in sediment, in landforms, in the chemistry of ancient air, you can hear the phase for what it is. A lull between larger movements. A calm interval between two slow continental breaths. The planet has been here before. It will be here again. In between those returns, it will keep doing what it has always done, quietly, steadily, reshaping itself with forces that don't need urgency to be powerful. And when you accept that Earth keeps doing this, returning, leaving, returning again, you start to see the present with a slightly different kind of clarity. Not because it suddenly becomes easy to predict the next 100,000 years like a simple chart. It doesn't. The system is too layered, too full of thresholds, too dependent on its own evolving state for that kind of certainty. But you do begin to see what matters. you begin to see which questions are the real ones. Not, will the orbit change? It will. Not, will the tilt keep swinging and the axis keep wobbling? They will. The real questions sound more like, what state will the oceans be in when the next period of weaker northern summers arrives? How much warmth will still be stored below the surface, waiting to be released slowly? Where will carbon be stored? Air, ocean, soil, sediment? And how quickly will it move? What will the ice sheets look like then? And what thresholds will they be near? What will the land surface look like? Dark forests, pale tundra, exposed shelves, flooded basins? Because those are the details that decide whether the orbit's nudge becomes a new ice sheet or fades into a mild fluctuation. And there's something else too. Something that doesn't show up in the elegance of orbital equations, but shows up in every core sample, every layer, every proxy. Earth is not obligated to change gently. Even though the forcing is slow, the response can contain bursts. In the climate record, there are episodes where temperatures shift more quickly than you'd expect, where circulation reorganizes, where the system seems to jump. Not instantly, not in a single year, but rapidly by geological standards. These episodes often occur during transitions, when the system is already under strain from a changing balance. In the North Atlantic region, for example, there are patterns of abrupt climate shifts tied to changes in ocean circulation and freshwater input events where meltwater or ice discharge can disrupt the formation of deep water, changing how heat is delivered to the north. These are not the primary beat of the glacial cycle, but they are part of the texture, the planet shivering and adjusting as it moves between states. This is another reason the glacial story doesn't behave like a metronome. The orbit is smooth. Earth's response can be lumpy. The planet can move slowly and then suddenly. It can drift toward a threshold and then tip. It can store tension in the form of ice volume, ocean heat, atmospheric composition, and then release that tension when a configuration becomes unstable. So when we talk about ending an ice age, we're not only talking about a gradual warming, we're talking about an unraveling that can include pulses, rapid retreats of ice margins, bursts of meltwater, jumps in sea level. Even a few meters of sea level rise, spread across centuries, can reshape coastlines and ecosystems more dramatically than most people realize. Because the world's coasts are shallow, and small vertical changes translate into large horizontal shifts. And when we talk about beginning an ice age, we're not only talking about snow lingering, we're talking about the slow establishment of a new stability, a world that becomes gradually more reflective, more carbon poor in the air, more oceanically reorganized, more seasonally biased toward cold retention. It is a different operating mode, a different resting place. At some point in a glacial buildup, the ice sheets reach a size where they begin to strongly influence the atmosphere above them. Winds shift around their domes. Storm tracks bend. Regions downwind become drier or snowier, depending on the pattern. Dust sources expand as exposed lands dry out. Snowfall patterns change in ways that can either feed the ice sheet's interior or starve its margins. This creates a kind of glacial geography patterns of wet and dry, warm and cold that are defined not just by latitude, but by the presence of ice itself. If you could stand on a glacial continent and watch the sky for 1,000 years, you would see the same storms returning along different routes than they do today. You would see seasons that feel familiar in sequence but unfamiliar in character. Colder summers that never quite clear the old snow. Winters that build and then hand their work to the next winter without fully surrendering it. You would see a world learning to become glacial, and that world would not be uniformly frozen. In many places it would be dustier. Winds would have more open terrain to sweep over. The air would often be drier. Some regions would be cold deserts, not because they are warm, but because there is too little moisture to sustain deep snow. Ice sheets don't need the entire planet to be wet and snowy. They need persistent accumulation zones and summers that fail to undo them. This is why, paradoxically, the deepest ice ages can coincide with dryness in many mid-latitudes. The cold locks water away as ice, lowers sea level, and weakens evaporation. Moisture circulations shift, rain belts move, the world becomes in many regions a harder place to be. And yet life persists. It adapts, it migrates, it concentrates in refuges. When the climate lines move slowly enough, species can track them. When barriers appear, ice sheets, deserts, drowned shelves, species can become isolated. Isolation can produce divergence over time. Reconnection can produce mixing again. Glacial cycles are not just climate cycles. They are engines that reshape the living map. Our own lineage moved through these engines. It's easy to speak of ancient humans as if they lived in a static prehistory, but they didn't. They lived in a climate that was often on the move. They lived with shifting coastlines and changing habitats. They lived with long arid phases and long cold phases and brief warmer intervals. Their roots were shaped by what ice and sea level made available. Their choices were shaped by what the climate made possible. And then, during a warm pause, agriculture took root. Settlements spread. The human world thickened into something complex enough to feel permanent. But deep time doesn't care whether a thing feels permanent. It cares whether it is stable within the system's long rules. And stability, on Earth, often means stable for a while. So when we return to the orbital story tilt, wobble, eccentricity, it's worth remembering what those cycles really represent. They are not just astronomical curiosities. They are the slow changing boundary conditions that determine whether the climate system is nudged toward a cold basin or a warm one. And because they are slow, they provide continuity. They provide repetition. They allow us to look backward and see the same patterns again and again. That repetition is why scientists can reconstruct climate history with confidence. It's why the sediment and ice archives make sense. It's why there is a rhythm at all. But the rhythm is not just an orbit story. It is a story about how Earth holds onto heat. Think of it like this. The sun supplies energy steadily. The orbit changes how that energy is scheduled across seasons and latitudes. The surface decides how much is reflected or absorbed. The atmosphere decides how much heat is trapped. The oceans decide how much heat is stored and where it is delivered. Ice decides whether the surface brightens and whether sea level shifts. Vegetation decides whether land darkens or lightens and how moisture circulates. These decisions are not made consciously, of course. They are physical outcomes. But the effect is the same. The climate system chooses a state based on how these components interact. In a glacial state, the system is biased toward keeping cold, higher reflectivity, lower greenhouse gases, altered heat transport, expanded ice. In an interglacial state, the system is biased toward keeping warmth, lower reflectivity overall, higher greenhouse gases, stronger heat transport to high latitudes, reduced ice. And the transitions between these states are where the system is most alive, most variable, most prone to pulses, most sensitive to small differences. That sensitivity is the reason the orbital cycles can matter so much despite being subtle. A small seasonal change, repeated, can push a sensitive system across a boundary. Once across, feedbacks do the heavy lifting. If there's a final thing worth holding on to as we move toward the end of this long exploration, it's the difference between the pace of forcing and the pace of consequence. The forcing, the orbital changes, moves with a calm, predictable slowness. The consequences, the growth of ice, the drop in sea level, the shift of ecosystems, the rearrangement of coastlines are enormous. That contrast is the heart of the mystery. How something so quiet can be so transformative. And maybe that's why this story lingers in the mind after you've heard it. Because it teaches a certain kind of deep time attentiveness. It suggests that the world is shaped not only by shocks, but by long, gentle pressures that never stop. It suggests that history is not only what happens dramatically, but what happens continuously. Earth has been doing that continuous work for millions of years, tilting, wobbling, circling, breathing out ice, breathing it back in again, writing and rewriting its own surface with a patience that outlasts anything we build. And if you listen long enough, you can almost hear it. Not a sound, but a rhythm. A steady, repeating movement beneath the noise of daily weather. A reminder that the planet's largest changes often begin as the smallest persistent differences, and that is how the forgotten Earth remembers. In the end, what stays with you isn't a single fact or a clean equation. It's a way of seeing. You begin with the simple picture Earth circling the sun, leaning slightly, turning through the year, and you end up with something much larger, a planet whose climate is shaped by geometry, amplified by feedback, and paced by timescales that make our ordinary sense of soon and late feel almost meaningless. And yet the logic is not distant. It's intimate. It's the logic of energy arriving and energy leaving. It's the logic of bright surfaces reflecting and dark surfaces absorbing. It's the logic of oceans storing heat and releasing it slowly. It's the logic of air carrying greenhouse gases like a thin, persistent blanket. It's the logic of threshold small boundaries that, when crossed often enough, become new climates. If you pull the whole story into one thread, it runs like this. Earth's orbit, tilt, and wobble slowly rearrange the distribution of sunlight. When northern high-latitude summers weaken enough, snow stops melting completely. Persistent snow brightens the surface and cools the region. Snow compacts into ice spreads, and the expanding ice begins to reshape winds, storms, and sea level. Oceans adjust their heat transport and their carbon storage. Atmospheric greenhouse gases tend to fall during the deepening cold, reinforcing the cooling. Over many thousands of years, the planet settles into a glacial state. Then the geometry shifts again. Northern summers strengthen. Melting begins. Dark land and ocean reappear. Sea ice retreats. The oceans warm and begin releasing carbon dioxide. Greenhouse warming strengthens. Ice sheets lose mass faster than they gain it, retreating in a long withdrawal that can include pulses and uneven collapses. Sea level rises. Coastlines shift. Ecosystems reorganize. The planet settles into a warm interglacial state. And none of it happens quickly. Not in a way a person can witness from beginning to end. The planet changes like a slow tide, leaving its marks in stone and sediment so that later minds can read them. That reading is what makes this story possible. Without the planet's archives, we'd have only the present, and the present is a narrow window. But the archives widen the view. Ice cores preserve ancient air. Ocean sediments preserve chemical signatures of temperature and ice volume. Landforms preserve the physical work of glaciers. Pollen and fossils preserve the migrations and disruptions of ecosystems. Together they reveal the rhythm and its variations, the way the planet repeats itself without ever copying itself perfectly. And the variations matter. They matter because they remind you that the climate system is not a rigid machine. It is responsive. It can reorganize. It can shift its dominant tempo, as it did around 1 million years ago, when the cycles stretched from 40,000 years to 100,000. It can linger, hesitate, surge. It can be pushed and then resist, or be pushed and then tip. That is why a future ice age can't be reduced to a simple countdown, even though the orbital cycles themselves are predictable. The orbit will continue to offer periods when northern summers weaken, but whether those weakenings become the start of a new glacial buildup depends on where the rest of the system is. On greenhouse gas levels, on the ocean's stored heat, on circulation patterns, on the condition of existing ice, on the land surface and the biosphere. In other words, the orbit is the schedule, but the planet's state determines the outcome. That's a subtle relationship, and it's easy to miss if you're only looking for a single cause. But once you see it, you start seeing it everywhere in Earth's long behavior. Slow forcing, layered response, gentle nudges, powerful feedbacks, the quiet turning of celestial mechanics, and the vast reshaping of continents. And if you let that settle, you may find the most striking part is not how cold an ice age can be, or how high seas can rise during a thaw. It's how much of what we think of as the world is simply one configuration in a long series. Our coastlines are not permanent. Our ecosystems are not fixed. Our stable seasons are not guaranteed on deep time. Even the ground beneath some regions is still rebounding from ice that vanished thousands of years ago. The planet is never finished. So perhaps the best way to end this long drift through glacial time is not with a prediction, but with a perspective. A reminder that Earth's largest changes are often the least theatrical at the start. The beginning of an ice age looks like a slightly weaker summer, a little snow that doesn't quite vanish, a brighter patch on the land. The beginning of a thaw looks like a little more melt at the margins, a slightly darker surface showing through, a little extra warmth held over into autumn. No trumpets, no obvious line in the sand, just a slow bias leaning one way or the other until the world has quietly remade itself. If you ever feel impatient with slow processes, this planet is an antidote. It shows what happens when pressure is applied gently, continuously, for a very long time. It shows what happens when small differences are allowed to accumulate. It shows that time is not only a background, it is an active ingredient. And that is the echo I want to leave you with. Not fear, not certainty, not a date on a calendar. Just the sense of a living world that keeps time in ways we rarely notice, tilting, wobbling, circling, breathing, moving between ice and warmth with a steady rhythm that predates us and will outlast us. Echoes of the Forgotten Earth doesn't end so much as it fades, the way deep time stories always do. Not with a sharp goodbye, but with the feeling that the planet is still turning, still balancing its budget, still gathering the next long season in its quiet hands.